Okay, today we're going to be looking at guided bend tests for welding. Guided bend tests are a very common destructive tests for evaluating the fusion of a weld. So how well the weld fuses to the base metal. Bend tests are done out in industry and they can be done on literally hundreds of different types of welds. So it's important to know what kind of weld you're doing and what standard you're testing that to. So let's start with that. The two welds that we do this on in my classes are a 2G or a horizontal groove weld with a backing strip, and a 3G, which would be a vertical groove weld with an uphill progression, also with a backing strip. We do this with the SMAW or stick welding process with a 7018 electrode. Our standard that we test to is the AWS, American Welding Society SENSE program standard. And that is based pretty much identical to D1.1 structural welding code. So if you're familiar with that, it's going to look the same. Like I said, this can be done on many different types of welds. You could use MIG, you could use an open root versus a closed root. All kinds of different variables that you can throw at this. The problem is all of those things would change how you'd set things up, how they would be welded. But what doesn't really change is that the testing process is pretty much the same. Okay? So in terms of how you're cutting the coupons, how you're bending them, unless you're starting to get into different thicknesses of metal and just variables that would change the testing process. So keep in mind, you do want to base this off a standard. If you're going to have your own in-house standard, that's fine, but then set that standard and let the students know how they're going to be evaluated and keep it consistent. So this document is straight from AWS Sense Program Guide. You can see this is ultimately what we're trying to do. We've got two separate pieces of metal here. We cut bevels on both of them or on one of them, depending on the weld that we're doing. We tack them to a backing strip. Now here they show the backing strip being flush. I like to extend my backing strips out a little bit farther to have a place to start and finish the weld on. And then ultimately, we're going to be cutting these testing strips, one out of here, and bending them to test the quality of fusion at the weld joint. For years, we did this exact same thing with both our 2G and our 3G uphill welds. We did it just like this because, well, that's the document that Sense gave us for a diagram on how this was supposed to be done. But further on in one of their guides, they give a technical process sheet, which gives a little bit more detail on the welds. And that actually specs out a slightly different joint for the 2G. So we switched to that. And it's going to have us do a single bevel instead of a V groove. And the only difference would be a single bevel. We only bevel one piece of metal with a 45-degree angle. And we leave the bottom piece flat. And ultimately, that means that we're going to have a 45-degree angle on one side, whereas a V groove, we're going to get a 22.5 and a 22.5, and they're going to add up to 45. But that's a very common weld for or a joint fit up for a 2G. I'll show you that on the next page here. So you can kind of see the fit up on a horizontal weld. We were welding horizontal across the joint. The plate is held up vertical. And there's our welding symbol depicting a single bevel with a backing strip on there. So you can see the bottom piece is not beveled at all, but the top piece is. So that's kind of the setup for 2G. And this is a welder performance qualification technique sheet, which is kind of wordy, but it's a variation of a WPS, if you're familiar with that, a welding procedural specification. It's going to give basic variables that the welder can use. So we're going to weld this on 3/8 thickness. It has to be ASTM 836 plate. If you're not familiar with your different grades of material, you can certainly look that up, but it's your common structural welding material. If you call up your supplier and ask them for a piece of angle iron or a piece of flat stock steel, they're probably going to give you 836. But specify, if you're doing bend test, specify so you make sure. Position 2G. Doesn't really have a minimum preheat 50 degrees. So unless you're keeping your metal outside, there really isn't a preheat, and no maximum inter pass temperature. We can clean with a wire brush or grinder as required. carbon steel backing strip. The coupon is going to be 3/8 inch thick, 3 inches minimum for each side, 7-inch total length. So we buy 7-inch stock. And then they give us some variables depending on what the student wants to use, what they're comfortable with. They can either choose a 3/32 electrode, an 1/8 inch electrode, or a 5/32 electrode. Typically, my students will run 1/8 inch electrodes. Every once in a while, I get a student who wants to run their root pass with a 3/32 and then switch to an 1/8 inch for their fill and cover. And that's fine as long as they stay within the variables. So you can kind of see here, we've got your amperage range for a 3/32 between 70 and 110, between 90 and 150 for an 1/8 inch electrode. I typically don't have anybody run a 5/32. We have a few electrodes on 5/32, but we just don't run them as often. But certainly would save you a little bit of time if you jumped up with that. Stringers or weaves, again, if you're not familiar with that, we don't have time in this video to go through welding techniques for these processes. That would be a whole separate video. But ultimately, stringers, multiple beads kind of stacked in there, where a weave, you would do one big bead going across the weld, and then again another layer, one big bead going across the weld. Typically on a horizontal joint, we're going to do stringers, and that's what I teach, and that's usually what my students will do. On a vertical, we'll kind of teach both. I do both of those and have the students pick what they're comfortable with. So here's the vertical sheet, similar thing. Again, we're doing a 22.5 degree bevel on each side. We've spec'd out a 1/4 inch root opening, and it's going to be a progression of uphill. That means we have to start at the bottom and work our way up. I wish they would change this diagram and have it standing up on our page, but they have it laying down. But yes, you do need to work from bottom up. You cannot run vertical down on this particular WPS or this particular test that we run. Could you do a vertical down weld with maybe like a 60-10 or something? Sure. But again, that's a different procedure. So I'm not speccing those out. Again, we've got 3 different electrode choices as far as size, all running a 7018, which is a very common structural low hydrogen electrode. Your amperage ranges are going to be about the same. They can, again, run either stringers or weaves, whatever they're comfortable with. Okay, and here's how we set up our base metal. You can see I buy 3/8 by 7-inch, just flat bar stock, 836 steel. And we've got a couple different ways that we'll cut it. Sometimes we'll take our pieces right to the bandsaw, okay, and we'll cut them right at the bandsaw. That's effective, especially if you're doing practice pieces. I don't have them cut them 3 inches long for practice. I'll have them cut them an inch, 1.5 inch for practice, and they'll have bevels on both sides so that they can just keep putting another piece on the end and another piece on the end, and until they practice this joint several times. But more often than not, if they're doing test coupons, I'll have them take it over to the iron worker, and we'll cut out like a 7.5 inch piece. And then we'll set our bandsaw at the correct angle. So 45 if we're doing a single bevel for a 2G, or a 22.5 if we're doing our a bevel on each side for the VG, or the V groove, sorry. So you can see this is how we would cut that piece. It comes out of the bands, or out of the shear, about 7.5 inches. We'll find the center, and we want to cut it right down the middle so we get equal pieces. This would be for your 3G, because you end up with then a 22.5 and a 22.5. If you're cutting this for a 2G, we would have to cut one piece square on the end to make sure that we have a true bevel, single bevel versus a V groove. And if you're not familiar with that, you got to touch up on your welding symbols a little bit. Again, we don't have time to go into everything. But notice I have these arrows on here. The arrows indicate the direction of extrusion on that plate. It's very important that you cut your bevel across those arrows so that when you bend this, any alignment of the grain, we got to think about grain in metal kind of like we think about grain in woodworking. The grain goes lengthwise with the extrusion, so it's going to be stronger that direction. If you cut it the other direction and the length of extrusion is parallel to your cut, that means when we go to bend these, your your grain lines, the weak part of your grain is going across the bend, and it's more likely to fail. So you could have a perfect weld, but because the crystalline structure of the metal is set up lengthwise going across your bend, it's going to be more likely to break instead of bend. So very important. You could fail a bend test just by cutting the metal the wrong way. If you're doing this in industry, you're probably ordering coupons from a company, and they're probably stamped with a heat signature, what grade of metal they are. There's probably a serial number that goes along with it. We cut our coupons in-house and do everything in-house, but it is important to make sure you do it the right way. If you don't have a bandsaw that tilts at an angle, you can do alternative methods of cutting. So I created this jig for cutting with our handheld plasma cutter. And this one sets it up at a 22.5-degree angle. I just take my other hand, and pinch it right here with my thumb on top of this piece of cold rolled, and I'll just simply slide it all the way down. It takes a little bit of practice, but honestly, if you get good at it, you can cut coupons way faster than you can on the bandsaw. They do require a little bit of cleanup, though. Bandsaw cuts them pretty clean. You don't really have to spend a whole lot of time cleaning up the actual bevel itself. But it is possible to do it either way. After you cut your coupons, I do like to clean them up. We have a belt grinder that we'll take, and I'll clean the actual bevel itself, and just kind of start at the top and just slide the piece all the way up, get all the way down to the bottom. And then I'll take mill scale off both the back side and the front side. You don't have to take the mill scale off, but I highly recommend it. It's going to make a much cleaner weld. You're going to get less chances of it's going to help with several things. Undercut, for one, on the front on your cap. If you've got mill scale on there, you're more likely to have undercut. It's not a guarantee, but again, you want to try and do this right, and the right way to do it would be to take that mill scale off. Mill scale melts at a much higher temperature than steel. So even though it's a very thin layer, it can cause some problems as you're welding. So since this is a test, go ahead and do it. Put your best foot forward and get that mill scale ripped off. So you can see I set this down on my table, and most of our weld tables have spatter and all over them. Yes, the students do try and grind that off eventually, but you can see the table is not going to be very flat. It's not going to be very smooth. So I always have the students put it on a flat piece of cold rolled. We've just got a few lying around. They'll set that on top of their table as a nice flat surface. The WPS calls for a 1/4-inch root opening. So all we do is take our backing strip, and we just stand it up on edge. Our backing strip is a 1/4 inch by 1 inch. So you can see I get my bevels. This happens to be the 3G weld. I'll get my bevels set up so they're just perfectly flush with each other. And then I'll slide them apart and put my backing strip in there, pinch them tight together, and I'll clamp both pieces to the table. Once both pieces are clamped to the table, I remove the backing strip. Notice how I also remove the mill scale off one side of my backing strip. The back side I don't care about. The side that I'm going to get welded against, I want the mill scale off of there. Once I do that, I'll take the backing strip and I'll kind of mark it with soapstone so that it's centered on my groove. I'll slide it forward, mark the other side, and then I'll make sure that I have enough hangout over here with my backing strip, and I'll put another clamp on top of that. Important, you do want to clamp that down as well, so you're going to get 3 clamps, and then I'll tack my backing strip on. I like to tack fairly hot. I'm at 135 amps with an 1/8 inch rod. That's kind of minimum. I'll even go up into 140, 145. I like to make my tacks quick. So when I tack the coupons together with a backing strip, I like to have those tacks as far to the outside as I can. You can see even this tack got a little too far in for what I like. I like to have them on the outside a little bit. So the reason being, we don't want those welds in our test coupons, which get taken out about 1 inch from the edge starting, and then about 1 inch from this edge. So if you can keep your tacks outside your test coupons, that's one less thing that you have to worry about, that heat affected zone from the tack, and just grinding that off, cutting that off afterwards. It's one less thing to worry about. This is kind of neat. I thought I'd show you this too. I started doing this year with my earplugs with the students. I used to have foam earplugs and they'd get all over the shop. And I bought the ones with strings on them this year, and they just attach them right to their helmet. And that way every kid has their own earplugs, and they can't, they're not going to lose them. They're attached to their helmet. So after we weld up the test coupon, we go ahead and we punch a couple things on it. We always punch them in my class upper right hand corner. So for a 2G, it's going to be right here. And for a 3G, it's going to be right here. I'll also stamp it with the student's initials, so I know who did that weld and what position it was done in. It's also a quick reference for me. When I walk into a booth and a student's ready to make a weld, I can quickly look at where the stamp is. If the stamp all of a sudden is in the bottom left corner, well, they've got it upside down. And for any weld that they're doing, it has to remain in the same position for every bead they run on it. They can't flip it, you can't run a bead, then flip it upside down, and run a bead and flip it again. It has to stay in the same position. So it's a quick reference for me. I don't have to sit there and analyze the bead. Okay, I can just say, yep, they've got it in the right position each time. So again, 2G, there's my 2G stamp. This is how it's going to be set up. You can see the bottom piece is not beveled here. The top piece is beveled at a 45. You can see I've ripped the mill scale off around the front. You don't have to take the mill scale off the entire plate, just around the front of the weld, and then around the back, same thing, and on the back side, just where the weld's going to go. Here would be my 3G if this were 3G setup. It's not stamped yet. It's just kind of hanging out there. I'm holding it for the picture, but I would have a 3G stamped up in the upper corner right here. And again, I wouldn't clamp this one in here. I'd clamp it up higher so that they can actually start on the backing strip and work their way up. Use that backing strip to kind of preheat things as they go. Same thing you can see in the 2G. They're going to actually start welding out here in the backing strip to get that nice and hot before they tie into their weld and make it out, and they can run out on the end. So after they run their root pass, I'll do an inspection. And notice I'll have this one marked as hot, and I've got a picture of a water tank here. Now, experts will say, hey, don't quench. Never quench a bend test, because you're quenching it, you're going to harden that steel. And yes, that's kind of true. Ultimately, it's A36 steel. It's not really heat treatable. There's not enough carbon in it to really do much, even if you do quench it. But you don't want to take any chances. So if this is a bend test you're putting a lot of time and energy into, and you want to pass it, let it cool naturally. Let it sit. For your vertical welds, I didn't point it out on the WPS, but there is an intertemperature pass heat temperature, so you want to let that cool down on your vertical welds in between your passes. It's to the student advantage to do that. On your horizontals, I like to run them as hot as I can, and I'll just rip those across. But the vertical ones, you definitely want to let those cool down. You can use a little temp guns. You can use a crayon, temperature-sensitive crayon temp sticks. They're kind of expensive, but if you just get one that's 20 or 30 or 50 degrees lower than the maximum interpass temperature, you just rub it on there. If it melts, it's too hot, and you can kind of let them cool down a little bit. But they recommend not quenching it. But again, it's A36 steel. It probably won't hurt it. So if a kid accidentally quenches theirs, don't make them throw it out. Just go ahead and test it. So one of the things I'm looking for as the students are welding this, I want to check their fit up. I want to check their root pass. And then ultimately, I want to check before they weld each subsequent pass. We're going to have a root pass. We're going to have several beads or layers if they're doing weaves within the fill, and then they're going to have their cap. So to make sure that students aren't cheating, doing this out of position, doing this, having another student do it for them, I tell them I have to see them start every bead they run. I may not watch the entire bead. I've got multiple students in a lab at a time, but they can get it cleaned up, chipped, brushed, wire wheeled, whatever. They get ready for that next bead, and then all I have to do is say, Mr. Moore, I'm ready to start my next bead. And I pop in their booth and I say, yep, start it. I check to make sure that they're in the right position. They're using the right rod. They're using their bend test has their name on it. And then they run that bead. And I start them. I watch them start the arc. And in some cases, if I need to give the kid feedback, if it's something I want to watch, I'll stay there and watch them weld that particular bead. Typically, when they're at the point where they're testing, I'm done really giving them an evaluation on each individual bead. So I may jump to another kid's booth, have them start a bead, jump to another one, and just kind of keep going around the room like that. And then they're going to have some chip time, some clean time. But every bead they run, I watch them start that bead, so I know they did the bead. It was done in the correct position. It was done with the correct setup and rod. And then ultimately, at the end, after they've run their cover pass, things have cooled, then we'll do the visual inspection of the final weld. So the visual inspection of the final weld, that has to be inspected prior to bending. So there's a couple different inspection points on this, and that's what we're going to cover next. So this table 8.1 visual inspection criteria for level 1. This is from the American Welding Society SENSE program. This is what I use to inspect the weld. So I'm going to run through this first, and then we'll show you a little video of an actual weld that we can inspect. So first of all, we're looking for any cracks at all. Any cracks, and again, this is prior to bending, after they finished welding it and it's cooled to room temperature. If there's any cracks on the surface of the welds at all, or any cracks that are visible, automatic fail for the bend test. Now, it's not necessarily a fail for grade. I have to talk about that a little bit. Obviously, we're teachers, we're giving grades. We're giving evaluations based on a standard. So they may get a B on a bend test, but it didn't pass AWS standards, so they didn't actually pass according to AWS. But for a grade, they might get a B just because they didn't pass for one minor little thing. So I do have a scale that I use for students to see what grade they're going to get, and they are graded on several different things: their fit up, their visual inspection, their root bend, and their face bend, and then each one has a criteria for what grade they're going to get. But in terms of AWS, any crack at all or any incomplete fusion, okay, automatically fails that sample before we even bend it. So incomplete fusion, how do you measure that? Well, ultimately overlap. So where the metal rolls over the side and extends past your toe, that's really a big no-no. And even though you can't necessarily see the fusion, if you have overlap, there's a good chance that you're not going to have fusion there. No incomplete joint penetration and groove welds except where partial penetration groove welds are specified. Well, this is not a partial penetration groove weld, it's full pen. So we can't measure penetration with the backing strip on there, but we can also look for things like underfill. So if their cap is below the surface of the base metal, well, it'll be underfilled. That's going to fail a weld as well. Undercuts. Undercut is where we dig into the base metal next to the toe of the weld and never fill it back in. Very common on the top side for a horizontal weld because gravity's pulling that liquid metal away. But undercuts shall not exceed the lesser of 10% of the base metal thickness or 1/32 of an inch. Well, with 3/8 of an inch base metal thickness, 1/32 of an inch would be the lesser. So that's our standard we use. We'll check undercut, and it can be up to 1/32 of an inch undercut. Face reinforcement or root reinforcement shall not exceed 1/8. Well, again, this is a backing strip weld, so we can't measure root reinforcement like we can on an open row weld. But face reinforcement, this is probably one of the harder things that students have a hard time passing, not getting that bead too tall off the base metal. We'll talk more about that in the inspection videos. Number 5, no single pour shall exceed 3/32. So we're talking about porosity. Every once in a while, you get some porosity with stick welding. Oftentimes on a restart where it's cold, you might have some porosity. You're allowed porosity. You're just not allowed porosity that's bigger than a 3/32 diameter. So we'll look for porosity as it shows up. And it says number 6, where visual examination is the only criteria for acceptance, all weld passes are subject to visual examination at the discretion of the test supervisor. And again, this is not the only criteria for acceptance. We're going to be bending these. So for a weld that you're using just visual examination and you're not doing a destructive test on it, then it's kind of at the discretion of the test supervisor, in addition to criteria 1 through 5. So when I'm inspecting them, I'll go through and I'm looking for these things, and there's an inspection sheet that the SENSE program gives me. Typically, I'll fill this out after the fact. I've got my own kind of list that I'm going through in my head as I'm doing this. And then once I get one that maybe isn't acceptable, I'll write that down and then fill this sheet out afterwards. But we're not doing a size on this particular weld. So like a fillet weld, if it calls for a minimum size, we want to check that. Undercut, is it acceptable, rejected? Porosity, diameter, the largest pore, acceptable, rejectable. Overlap, if there's any overlap, it's unacceptable, it's rejected. Penetration, we can't necessarily measure penetration, so that one gets skipped. Appearance, this is where the inspector kind of has a little bit of input in there and in their opinion on the appearance of the weld. If the appearance of the weld isn't good, one of these other things is going to throw a red flag. But in some cases, you get, man, they're just squeaking in there, but weld looks incredibly rough. It just doesn't look like a professional weld. You can reject it. And then obviously the most severe would be cracks. Any crack at all, even the tiniest little bit of crack on a weld prior to bending. We don't like cracks because cracks propagate, meaning cracks as the material is stressed, cracks will grow. So if you've got a part that you put into service and it has a tiny itty bitty little crack on it, if it's being put under load, that crack's going to grow over time. If it's a cyclical load where you're like a bridge, we have cars going over it, and then there's no load, and there's load, and there's no load, okay, it's going to be worse and it's going to be faster, and that could be catastrophic. So cracks are bad. Ultimately, this is the sheet, and now let's take a look at a little bit of that video of inspecting the weld. All right, so we're going to start with some basic weld inspection from this 2G weld. And the first thing I do when I look at a plate a student gives me, I'm going to just kind of in general look at the weld, look at the shape of the beads, look for any potential problems of lack of fusion, looking at if there's any potential areas of underfill where they just didn't have enough reinforcement out on top, if it was still subsurface below the base metal. In general, this one looks fairly decent. There's 4 beads there. Okay, this is a horizontal weld, so this would have been the bottom, this would have been the top. Okay, they would have done this bead first, second, third, working that progression up. You can see this is the last bead because you can clearly see the entire bead there. Notice a little bit of undercut at the top. That's something we're gonna look at, and we're gonna measure that. And that's very typical, very common on a horizontal weld that we would have undercut at the top. Something else that we look for is at the bottom. Conversely, we might have some overlap where gravity pulls that bead down and rolls it over. But in this case, there's nothing. Everything looks good here. We do have this little tiny bit of a spatter there, and I know that spatter just from the weld itself. This is not an arc strike, and just because I was present for this being welded, and we talked about this, but this particular piece of spatter, let's say it was down here, and let's say I could see a trailing spark pattern or arc strike on there. That would be a significant thing to look for, even though it doesn't appear to be that big a deal. Oh, we can just grind it off. Grinding off an arc strike doesn't really solve or fix any problems. What happens is you have a localized heat affected zone. So it heats it up very quickly and then subsequently cools that metal incredibly fast because the thickness of the plate, okay, just absorbs that heat so fast because it's such a small area. You get a really quick, rapid cooling in that spot. And that, on a structural member, could be a critical thing that creates a stress spot in that metal. So that's why they don't want to see arc strikes. We want to look for those. In a typical certification test, an arc strike would fail automatically. Any weld, doesn't matter how good the weld is. But overall, it looks pretty good. So the next step I would go would be to check the reinforcement height. So instead of checking and measuring every single point on here, all the high spots, I'm simply going to take my VWAC gauge and we're just going to set that up. Try and get the reflection out so you guys can see. I'm going to set that at 1/8 of an inch, which is my maximum reinforcement height. There we go, 1/8 of an inch. Okay. And I'm going to lock that in, make sure it doesn't move, and then all I do is just slide over the top and make sure that I'm clearing everything. All right. So any high spots, I'd want to identify those first and just kind of check and make sure that that 1/8 inch is completely clearing. I check in both directions, and the plate does get warped a little bit, during that process. So, identifying where are the highest points and then going from there and kind of checking those. And this plate is great. There's hardly anything to look at in terms of excessive reinforcement. It's all sitting at about 1/16 of an inch or less. One area that I noticed though is I'm looking right down the middle of this where it does look a little bit recessed from these two beads here. And I want to check that for potential underfill. Underfill is where the bead just didn't quite come up to the surface of the base metal, and that's not a complete joint then at that point. It would not meet criteria. So even though they don't specify underfills in the criteria, the joint does need to be complete. So that is a big one. So all I'm going to do is use my VWAC gauge, and I'm just going to now push down into those low areas that I see and make sure that I'm still above 0. And anything down here would be above 0, so I'm definitely just barely over base metal thickness. So we're good. There's no issue with that low spot. I can check a couple other ones. Again, we're right at 0 there, so that would still be fine. And as long as we don't dip down below, we're good. So checked a few areas. Everything looks pretty good there. Next, as long as I've got the VWAC tool here, I'm going to go through and check undercuts. So again, if you remember, I'm going to turn it this way so we can kind of bounce some light off there and maybe see that a little bit better. Sorry, I have it the wrong way. Try that again. We can see those edges right up at the top there where there's just a little bit of undercut in there. Okay, so all I'm going to do is, again, put my VWAC gauge on, push the point down into the undercut, and we're going to take a look at that and measure it. And in this case, okay, we are less than the maximum allowed, which would be a 32nd of an inch. We're barely a 64th. So I just check each spot for undercut where there's any undercut exists in the weld. So far everything's checking out. It looks like a pretty good weld. Notice the backing strip on these. Okay, I like to see them weld out onto the backing strip at the beginning. It helps heat things up a little bit, helps get that plate warmed up so that you don't have a cold weld when you're first starting. Same thing, finish out onto that backing strip, okay, allowing you to make that weld to the end. You're always going to get a little melt back on the edges. I don't check anything within about 1/2 an inch of the edge. You're going to get that. And that's not a big deal. So overall, this looks like a pretty decent weld. It does meet the acceptable criteria for the 2G bend test according to the SENSE standards. Again, really depends on which standard you're measuring to. If you're going to go to D1.1, again, it's very similar to the SENSE program. They use D1.1 as a reference. But if you're welding to certain other standards, it might not allow any undercut. So you kind of have to look at that and pick a standard. You can develop your own in-house standards as well, but do set that standard. Know what the standard is prior to inspecting. Make sure that the students know and understand that. Okay, here's another example of a vertical plate. This was a 3G vertical. This plate was actually fitted up and stamped as a 2G. However, it was a V-groove instead of a single bevel, and we just rotated it and used it as a practice plate for a 3G. This doesn't count towards a test because it was the original root pass was actually run 2G, and then I said, wait a second, that's the wrong fit up. We've got to fix that.
So anyway, this is a 3G weld, and I pointed this one out for a couple reasons. One, we've got an arc strike here. So again, you could sand that with a flap disc and get those marks out so it looks like bare clean metal. But if you were to do that and then take an acid etch and etch over the top of that, you would see a heat affected zone in there. Again, we're changing the grain structure of the metal in that spot, so that's a bad thing. The other thing I want to show you is this is a weave weld, okay, versus stringers. Stringers would be small narrow beads stacked next to each other versus weaving the electrode back and forth. Now we can see on this one, overall it's not horrible, but we've got some restart issues. So there was a weld done here and then a new rod clipped in and a restart up to here, it looks like, and there's another restart. So the restart didn't come down quite low enough on the right side here. And so if I measure that with a VWAC gauge, in that portion we're a good 1/16 of an inch below base metal. So that would be an incomplete joint. You know, depending on what code you're looking at, if this were a weld done on a job, sometimes there's allowable percentages that they could leave in there for certain things. But on a bend test like this, that's going to fall right within the path of the testing piece that we're going to actually bend. So that's not going to cut it. Up here, the tie-in's not quite as bad. I think we're probably pretty close to flush with that one with base metal. Yeah, right on zero there. Hard to see, but there we go. So again, just wanted to show you the difference according to the welding specs on this particular weld. They can choose stringers or weave. They can also choose their electrode size. So students will ask me about the reinforcement piece quite a bit because it is challenging. This, well, what's the big deal? If I have more weld, isn't it stronger? The reason we don't want that excessive reinforcement has to do with stresses on the metal. If I have a bead or several beads, okay, for my cover pass, and those beads are kind of coming in at a fairly steep angle to my base metal, and I'm just making the original joint, which was a V-groove in that case for the vertical one. So the steeper this angle, the closer this gets to 90, okay, the more stress is going to be applied right here at the toe of the weld, okay, right in this location. As the weld bead cools and shrinks, massive amounts of stress build up here. As opposed to, say, a weld that has maybe a little lower profile. Okay, the angle is significantly wider up here and more gradual, way less stress accumulating at the toe of the weld. So that's why when we look at a code, we look at reinforcement is kind of a big deal, even though on the surface it seems like it's, you know, going to add more strength to your weld. It may add more strength through the throat of the weld, but it adds a lot more residual stress to the base metal right here. So that's why that's in the code, and that's one of the things we look for.
Okay, so now after we've inspected the weld and it passes visual inspection, or even sometimes if it doesn't, a lot of times if a student just wants to bend theirs, even if they didn't pass visual inspection, we'll still bend them, especially if it's their first one and they don't have anything for a score for the gradebook. Again, just because they don't pass for AWS doesn't mean I'm not going to give them a score in the gradebook. So we still want to bend these in some cases. Sometimes they already have a score in the gradebook and they bent them and they're just trying to pass the overall qualification for AWS. Well, then they might not want to waste the time cutting the coupons and getting everything prepped. So you can see how we cut them. The coupons are laid out from the center line. We go over an inch. Okay, we take an 1.5 inch coupon. We go the other direction, go an inch, and take an 1.5 inch coupon. I'll talk about it in the video of me doing this, but I do like to cheat this just a little bit. I'll go more like 7/8 of an inch and 7/8 of an inch, and I'll still take that 1.5 inch coupon. That way the center piece can be used as a substitute coupon. It's a little bit smaller. It's not quite that 1.5 inches. It's a little bigger than that, but smaller than 2 inches. And we can use that as a backup coupon if, for example, when we're cutting backing strips off, we gouge into the base metal. or if we grind a little bit of the excessive weld reinforcement off and get a little bit too carried away with the grinder, we can substitute in a piece for that. So, but let's take a look at the video of going ahead and prepping that for.
Okay, so we've got everything marked out. A few different ways we can cut this. We could take a torch. We could cut it with a torch. We could cut it with a plasma cutter, whether it's on a track system or handheld. If you're doing handheld, torch, or plasma, I'd recommend a straight edge of some kind so you can kind of keep those edges nice and straight. So you can do that. It's probably faster than saw cutting, but it's not as accurate, and they're typically a little bit more cleanup. So what we do is we're going to cut these strips out with our horizontal bandsaw. There's a little trick to it, depending on what saw you have. You could cut it with a vertical bandsaw, but I'm going to show you how we set up our horizontal bandsaw to do this. After we get the strips cut, then we're going to tip it up and cut the backing strip off with a torch. Some people cut it off ahead of time. It's just a lot more torch work. You've got 7 inches of backing strip to remove versus 1.5 inches and 1.5 inches. So I like to cut the backing strips out afterwards, which is another reason why I like to cut it out with a saw, so that you don't have that extra thickness to deal with. So let's go cut it on the saw. All right, so we're out at our horizontal bandsaw. We have to make a slight modification to our saw. The plates aren't going to cut very well if we stand them up vertically because they're not flat. They just tend to sit there and vibrate, and we've got blade issues. If we lay them down flat, you guys know, trying to cut through a piece of 7-inch metal laid down flat, you don't have enough tooth pressure to get through that, and you're just going to sit there forever and dull your blade. So we found putting it at an angle is the best. So there's a couple of holes in my fence right there, and we just simply took a piece of angle iron, welded some threaded rod. We use a couple of wing nuts on the back, and that attaches right to the fence. It's pretty easy, pretty quick. The next thing we need to do is just slide our guard back a little bit. Cutting a wider piece, we just need to get a little bit more room in that blade. And we should be ready to rock. So I'm going to take the bend test, put it in there. We're going to cut the first 3 lines, and then we're going to flip it. That last cut gets a little bit tricky. Okay, so I've got that last cut set up in there. The last piece gets a little bit too narrow for my clamp to actually clamp onto. You can see it's a little bit shorter there, just kind of lined up. So I simply just use a filler piece in here, clamp it down on this end to lock it in place, and then push my clamp against it here, and my part butts against there. Okay, so I'm set up for cutting off the backing strip. This is typically how I do them. I'll stand the pieces up on edge. We've got the 1/4 inch by 1 inch backing strip here. And I'm simply going to take an oxyacetylene torch, starting at this corner, and cut all the way across. I've done this with plasma before. The problem with plasma is it'll jump an air gap and it'll gouge in your part with very little effort. So it's faster, but typically end up ruining more bend tests than it's worthwhile. So with oxyacetylene, because there's a slight air gap between my backing strip and my base metal, at least on the left side and on the right side, if you accidentally tip the torch towards the base metal, you won't actually cut into it. It's kind of like taking your cutting jet lever, pointing it at metal that isn't preheated and hitting your oxygen jet. You won't cut through it because it's not preheated. That air gap prevents that from happening. The problem is in the center of the backing strip, ideally they weld it into the backing strip and fuse that there. So there's no more air gap, so you do have to be careful as you cross through the center with the torch that you're not angling it back in towards the base metal. Otherwise you will gouge that. So I'm not going to actually film the cutting. I've tried filming a couple. It just doesn't show up real well. But I'm going to kind of show you how I do that. Instead of just preheating at the top of this corner, it's a pretty thick piece. I'm set up with this big gouging tip. I'm running about 60 psi on my oxygen and about 4.5 or 5 on my acetylene. Since that is a pretty thick piece, I'm going to actually start down here and I preheat at the bottom. Heat rises, so I want to preheat that bottom piece and I'll bring it all the way up. Kind of back and forth, get that hot. Then I'll tip my torch up and preheat that corner. It doesn't take more than about 2-3 seconds. It's on an edge. And I'll hit my cutting jet. At that point, it takes about a second or so for that stream to shoot all the way down to the bottom. And then I just brace my hand and I'll just walk that all the way across, trying not to gouge in the center portion. If you go too fast, you end up with kind of a hump down at the bottom. And that's pretty typical, but I'd rather go too fast and leave a little extra to grind off later than go too slow and gouge into my base metal and ruin a perfectly good bend test. So I'll just kind of walk that. If there's metal on the right or on the left, I can angle it back into the base metal. Just kind of wash that off all the way down. Won't hurt anything. Again, I just don't want to angle back into the base metal during the center of the backing strip. Okay, so this actually happens to be the center piece. I already cut the backing strips off the actual test pieces, so that's why it's a little bit wider.
Okay, so after the pieces are cut, we need to prep them to bend. Kind of tells us how we're going to do that. Anything that has a radius out here like this is cut from a piece of pipe. So again, we can do bend tests for all kinds of different welds, including pipe welds. We're not doing pipe welds on this, so we're looking at these more rectangular pieces here. So one is going to bend towards the face, one's going to bend towards the root. They're showing which area we're bending towards is shaded in gray. This chart's a little bit confusing, but what they're telling us is the finished coupon compared to the total thickness of our original base metal. And if we're doing some smaller, thinner base metal, we can get by with a slightly different thickness. But with 3/8 and over, basically we're looking at the TS is going to be the same as our base metal. It's going to be 3/8. Now, if we had a 1/2 inch thick metal, we could still get it down to 3/8 of an inch. But in this case, we're dealing with 3/8 of an inch metal, and that means our specimen thickness needs to stay 3/8. Now, that's important to look at because a lot of people will do this part kind of at their discretion. They'll grind until the undercut comes out. Now, you remember, you're allowed a 32nd of an inch of undercut. So if you grind your coupons down until there's no undercut, they're actually a 32nd of an inch undersized. Now, again, I don't see anywhere in here what the tolerance is for that. So let's say there was a 1/16 tolerance for how thick your coupons are, then that 32nd of an inch would be fine. I like to get them fairly uniform. If there's some undercut there, as long as it's less than a 32nd of an inch, I'll still leave it in there. If it's super minor and it's almost gone after we're done grinding off the reinforcement, then I will maybe take the rest of it off just to clean it up. But leaving the undercut in there isn't a big deal. You can do that. We're shooting for that 3/8 of an inch on our material thickness. So let's watch a little video of how we prep those. Oh, one more piece, I guess, before the video. We do want to have a slight radius where we bend those. So I just take here and grind a little bit of radius. Again, max is 1/8 of an inch, so we don't want to exceed that. But that helps prevent corner tears. If we leave it sharp, it's not going to want to bend. It's going to want to roll and rip right at that corner. And we'll talk more about that when we get into weld inspection or bend test inspection after we bend it. You are allowed to potentially have a corner crack, but anyway, let's take a look at that video.
Okay, I'm going to take a vice grip and I'm going to take these strips and clean them up on our belt grinder. It is important that the scratches you're putting in go with the length of the piece. Any scratches we want to go this way, back and forth that direction. We don't want any scratches going across this way. Tiny little scratches going across this direction are more likely to cause this thing to break open when we bend it. And so if you are going to use, say, a handheld angle grinder, you want to make sure that you're taking the disc across this direction so that the scratches go lengthwise and not this direction. And otherwise the scratches are going to go perpendicular to the workpiece, and that's bad for bending them. Okay, so I've got a bend test all ground down back from the belt grinder, and we're going to kind of take a look at it. But you can see a couple things right away. First of all, I ripped the mill scale off of everything, try and make it fairly smooth and uniform. Notice again the scratches all going the same direction, all going parallel to the length of the piece. Okay. I did also run the sides on the belt grinder as well to smooth those out from the saw cuts. Still a few saw cuts here and there, but again, just knocking it down, making it a little smoother. Also, the area where it bends, I took and rolled the edges so we have a slight radius there. Okay, we want to make sure there's a slight radius that helps the bend. You're allowed 1/8 of an inch. Okay. All right, so if we flip it over, you can see on the back right away, there's an area of concern. Right there, there's a faint little line. And you can kind of see some areas where it just didn't quite fuse.
Okay, so we've got our coupons prepped. We're ready to bend them. How do we do that? Well, there's a few different ways that we can do it. This is our bender. This is what we bought. This is what we have. I like it. It does have a drawback, and that's the coupons do pop out the top sometimes. And I wish it had a safety guard up here. There are very specific standards for how those bend test fixtures look and how they operate in terms of the diameter of the roller, the distance apart. You can see this one's adjustable for doing different thicknesses. And so here's what we use. There are some alternatives, and we could do a bend where we wrap it around a center point. And so if you've got like a diarco bender, you could rig up something with that. You just have to follow the standards. There's also a plunger type. So if you already have like a hydraulic press in your shop, you could certainly fabricate something or buy just the fixtures themselves to slide into your hydraulic press, and you could bend your coupons that way.
Okay, this is our bend tester. Pretty straightforward. We've got a roller. There are different positions set up for the roller depending on the thickness of metal you're bending, but this one happens to be set up for 3/8 plate. I did make a mark at the center of the piece, and you can see based on the bend of the part already that this would be the face. The plate warps a little bit towards the face. The sides pull up. So we're doing a face bend. I've actually already done the root bend on this, so I'll show you both of them when we're done. Here we go. And that's it.
Back to the actual bend coupons. So different criteria. We're no longer looking at weld visual examination. We're looking at bend test criteria. So no single indication shall exceed 1/8 of an inch measured in any direction. So what we're looking at is any crack, any porosity, any slag inclusion, any defect in the weld, or I shouldn't say defect, any discontinuity in the weld bigger than 1/8 of an inch, automatically becomes a defect and the bend fails. Okay. Now, if it's less than 1/8 of an inch, then we go to line 2. The sum of the greatest dimensions of all indications on the surface which exceed a 32nd of an inch, but are less than or equal to 1/8 of an inch, shall not exceed 3/8. It's kind of wordy, but what they're saying is if it's less than a 32nd of an inch, we just completely ignore it. So it could be a crack, could be a slag inclusion, porosity, lack of fusion area, whatever it might be. If it's less than a 32nd of an inch, we don't count it. There could be 30 of them. We don't count them. But if it's bigger than a 32nd of an inch and not more than 1/8, then we take all of those and we would add them together. And if they add up to more than 3/8 of an inch, then the bend fails. If it's less than 3/8 of an inch, then the bend passes. Cracks occurring at the corner, however, shall not be considered unless there is definite evidence that they result from slag inclusion or other internal discontinuity. So if you're bending it at the corner of the bend test, maybe it wasn't rounded over quite enough, and it cracks, and you can't see any slag in the crack, or maybe there's a porosity bubble right next to it, or maybe this is more common, lack of fusion like on the root bend where they didn't quite tie into one piece or another, and it starts and it cracks from there from the corner down, then it would fail. But if you don't see any of those and it's just a corner crack, okay, it's fine. Now, this is where there's a slight difference between AWS criteria and for the SENSE program and AWS for D1.1. D1.1 goes into more detail about corner cracks. If it's bigger than a 1/4 inch and we still don't see any evidence of any discontinuity causing that crack, then we can replace it with a different sample and bend that. They don't get into that in the SENSE program, but that is something that I still do. If we get a big crack in there, I'll just replace it with one of their other samples. Unless that crack is caused by a discontinuity, then it automatically fails. It doesn't matter if it's on a corner. So let's take a little video that shows inspection of a bend test.
All right, so we're going to take a look at the face bend first. And so here's my weld coupon. This one had 2 pieces that were a little bit different in size. This one was probably closer to 3.5 when they were fitted up, and this one was closer to 3. That's why I purposely made sure I bent it on the center of the weld, but that's why this leg looks a little bit longer. So just keep in mind that you really want to make sure you're bending it on the weld. If the weld happened to be up here, okay, and we bent it off to the side, that's not a successful bend test. That's another situation where if that happened for some reason, it's probably because of poor grinding, poor coupon prep after the fact. There's maybe grounded a little bit too thin in this area, and the weld happened to be up here or something. But in this case, the weld is right here. We can see that. There's a heat signature kind of down here. There's a little bit of undercut that never got ground out, which is fine. Again, we talked about that. You don't have to grind the undercut. The coupon should be left 3/8 of an inch. And you can see right in here, there's kind of that shadow line showing the other end of the weld. We have a little tiny bit of maybe undercut there that never got ground out, and another one right there that's kind of inner bead between passes. There might have been a little undercut at the top of one that never got filled in. But again, all those checked out prior to bending. They're all less than a 32nd of an inch. There's only one discontinuity we have right here after the bend that actually popped open, and there's a little tiny hole right there. And I did take a magnifying glass, put it on there. You can see a little tiny itty bit of slag. But again, we're looking at that, and clearly it's right about a 32nd of an inch when I measured. So a 32nd of an inch is that threshold. If it's less than a 32nd of an inch, then we don't count it at all. If it's more than a 32nd of an inch but less than 1/8, then we would add up the total. Well, in this case, there's only one. So regardless whether it's a 32nd of an inch or just over a 32nd, it's clearly less than 1/8 of an inch long, okay? And there's not multiple ones, so we don't need to add up anything. So this face bend would pass, okay? Problem is, in order to pass a successful bend test, you need to pass both the face and the root. So face passes, and for a grade, okay, I grade them separately on their root versus their face. But in terms of actual passing the bend itself, if we're looking at the SENSE program, they have to pass both the face and the root on the same bend test. They can't pass a root on one and then weld up another one and just pass the face. They've got to pass both. So let's take a look at that root. So again, we can see this is clearly the root for a couple reasons. We can see the heat signature here kind of ends. Might be a little hard to see on the camera. But right there, there's kind of a shadow line there. And then clearly we've got lack of fusion going on right here. You can see the original base metal. And so there's a nice straight line. And you can see the weld bead didn't actually fuse onto the base. So here's the base metal. Here's the weld bead on the root opening there. And just didn't quite get it in a few spots there. And since this one right there is bigger than 1/8 of an inch, okay, this one would fail. Okay. If we didn't have this particular one right there, okay, this one was a little bit smaller than 1/8. Okay, that one's smaller than a 32nd. Okay, that one's smaller than a 32nd. This one was about a 32nd. So even if we counted this one and this one, we would still be less than, okay, that 3/8. But then we get to this guy here again. It's a corner crack. So as long as we're not seeing any discontinuities, we can have it up to a 1/4 inch. But I do see lack of fusion there. Again, we got that straight line where it cracked right on there, right in line with all these other discontinuities. So, you know, that corner is not cracked from just having too sharp of an edge there. It's caused by lack of fusion. So that would automatically fail it. So again, we've got a root bend that did not pass. We've got a face bend that did pass. So for a grade, how I do it in the class is they're actually going to get several grades. They're going to get a grade for a fit up of the assembly. They're going to get a grade for the finished weld, so the visual inspection piece, and then they're going to get a grade for each bend. So they still might end up overall with all 4 of those grades having an A on this project, maybe an A minus. But in terms of passing for any type of credential, okay, this wouldn't pass. I still also do levels for grading. I do levels. So we're on a 4-point standards-based grading. So in order to pass a bend test with a 4, obviously it needs to pass for AWS standards. So then I go into levels of, okay, well, how did it not pass? Is it just barely not passing? Are we just adding up a total of small discontinuities and, you know, it just didn't quite pass? Then it's sitting at about a level 3, depending on a few other scenarios. Did it break completely in half and have 2 separate pieces? Okay, well, you're going to be sitting at a 1 for a grade there. Did it, you know, hold together, but it cracked, you know, almost all the way through, or lots of discontinuities, big slag inclusions, that kind of stuff? Then you might be at a 2, but it has to hold together in order to get a 2. So that's kind of my scale. That's what I came up with. Again, for any type of welding certification test, or in this case the SENSE program completion, they do need to pass both a face and root bend. It does need to be on the same piece of metal. You can't take them out of separate ones. So there it is. That's what we have. This was the 2G. We would do the same thing for a 3G test. Okay, I kind of wanted to show you what's going on with that root bend that failed. So this is our 2G. We've got a single bevel weld, so we're beveling the top piece of metal. The bottom piece of metal stays square. We've got a 1/4 inch root opening. We've got a backing strip. All right, and what happened on that particular fail was the weld was tying in very nice to this sharp corner because it is a thin edge, and the student tied in pretty well to the backing strip. But this thick piece of metal, okay, and gravity causing the liquid metal to kind of fall down created something like this. Okay, so we got a weld bead that looks something maybe like this on their root pass, where again they were tying in pretty nice to the top piece. Heat rises, so that's a bonus. Plus we've got a thin point right here which is going to melt fast. So good tie in there. Tie into the backing strip. The problem is this thick piece of metal, with the heat rising and going away from it, this edge right there never got melted fully. The metal might have been just kind of laying on top of it. We saw that tiny thin line there, but it never actually fused in at that particular spot. So got to make sure they run nice and hot on that root pass. I usually run somewhere between 120 and 130 on this 2G. Okay, again, this is a 2G test, so it's a horizontal weld, horizontal V-groove. On the vertical ups on the 3Gs, okay, I'll run those a little bit colder because heat rises, so I'll run those typically 105 to 110, maybe 115. Kind of depends on if I'm running stringers or weaves, but yeah, definitely got to run a little hotter on the horizontal welds there.
So after we evaluate the bend tests, I'd fill out some basic paperwork indicating who welded it, is it acceptable, is it not acceptable for both the face bend and the root bend. One thing I'll point out as far as documentation, I want to make sure after I cut those strips, actually I do it before I cut the strips typically, right after visual inspection, we'll take that stamp tool and we'll stamp in which one's going to be the face, which one's going to be the root. So after we put the white lines or put the lines on there for cutting, we know where the bend tests are taken out of, and we'll stamp them. We'll stamp them with 2G or 3G, depending on what position they were welded in. We'll stamp them with the student initials, and we'll stamp one on the face side and one on the root side so we know which bend it was. That way we're kind of keeping things separate. I don't have students do the actual bending unless I'm present. Nothing gets bent unless I'm there. So a student can't just turn in somebody else's bend test and say, yeah, I bent these, I passed, because I'm there for every bend test. It's a documentation thing. If these students are earning a credential for it, I want to make sure that they're the ones who welded it. It's their bend. Everything's documented. So then this form would be turned in with that. I'd put that in the grade book, and I'd also enter it into the AWS system. This bend test could be used for all kinds of different welds. You really have to look at how the weld is being applied and whether or not this particular bend test is going to work for you. You can develop your own in-house standards, but I would always recommend following some type of industry standard like D1.1 for structural welding code. It's very common. If you're using the SENSE program, stick with it, follow it. I've heard instructors say things like, well, we do the SENSE program, but we don't do that weld, or we have them do it different than that, or I let them, use a different electrode, or I let them do their bend test with wire feed. You can't do that. It's not the same test. It's not the same credential. The standards are set for a reason, and you got to kind of stick to that program. So if you've got any questions, please feel free, reach out to me, shoot me an email. If you want to talk on the phone, shoot me an email, send me your contact information. I'll call you. I hope this was informational, and thank you for watching.